Good. Then our next speaker is Mario Castañeda from Huawei, who will represent the THz project. I will reset my counter for you, Mario.
Sure.
So let's see.
So just for the time, Hank, how much time? Until what time should I? Okay, you tell me, right?
I will put a timer that you will see in the video.
Okay, excellent.
We have about 25 minutes, but we have a few minutes extra if you need it. So
okay, so let me share my screen. Yeah. Sorry. So good morning, good afternoon, everybody. Thank you for your attendance in this online workshop. My name is Mario Castañeda. I am a senior researcher at Huawei at the Munich Research Center, and I here have the opportunity to present on behalf of several partners within the THz project, several related work to ISAC. In this project, THz, I am acting as a task leader for a task on ISAC. And before I continue with the details about contributions from the several partners, I want to provide a small overview of the project. So here you can see what THz stands for. So terahertz industrial mesh networks in smart sensing propagation environments. The consortium is composed of a diverse set of partners all across Europe. I'm not going to mention them all in the interest of time. But we have from academia, research institutes, and several industry partners. Now, I briefly want to also highlight the THz concept illustration, which is in the setting of industrial scenarios. And here are the list of objectives. I'm not going to go over them. I just want to point out that among the enablers and the objectives within the project, we have integrated sensing and communication as an enabler and an objective, right? And as I mentioned before, we have this ISAC functionalities task, for which I have the opportunity to lead. And before I continue, I would also like to thank all the partners and contributors to this task and to this presentation. From Huawei, we have Ali Ghanem, Richard Sterling Gallagher, from the University of Stuttgart, Simon Hausmann, Dominic Anna. From Kenit, we have Tommaso Bacchielli, Andrea Giorgetti, Marina Lotti, Giulietto Alcolacci, and Davide Dardari. And from TU Braunschweig, we have Stefan Cruz. So before I start with the different parts that I would like to share with you today, I mentioned some basic preliminaries. Alain has also mentioned some of these aspects already. It's going to be quite a quick recap. I think all of you know what ISAC means, but there are different names for the same concept, and people have different understanding depending on the definition that is employed. But the point is that you can have joint communication and sensing or integrated sensing and communication in different combinations. But as also pointed out by in the previous presentation, I mean, what do we mean with sensing, right? So the idea is to get information about an object, usually it's passive, right? Or about the environment, right? Which is definitely passive, from measurements of reflected signals, right? This information can consist of the range, position, velocity, shape of an object or of the environment, right? And I think it's important to point out a difference or why is positioning not necessarily sensing, right? Because in positioning, you have, let's say in this case, a positioning of a user equipment, you require that the UE transmits or receives signals. That means the UE is active, right? So whereas with sensing, you don't not need to have the device to be active, right? It can be passive. So sensing can be performed in two basic setups. In a monostatic setup where the transmitter and receiver are co-located. In this case, you need full duplicate operation, right, to receive the signal that is sent and receive the same place. Otherwise, we have a multi-static setup, in this case, a bistatic setup where the transmitter and receiver are not co-located. So here's just an interesting example where we see that for positioning, for example, you make use of this line of sight, right? And whereas for the sensing of the object, you actually use this multipath component, which can also be used to position the UE, right? But anyway, like I said, this is the difference mainly with the passive sensing, where the object does not need to be transmitting anything. Now, regarding the presentation here at hand, so at terahertz frequencies, we assume we're talking about from 0.3 terahertz to 10 terahertz. These frequency bands are attractive because there's a lot of bandwidth available there. So we can have high resolution sensing, and also high data rates can be supported. But the high frequencies impose several challenges, right? So among the challenges we have we have a higher sensitivity to radio frequency impairments. In addition, in the industrial setup that's considered within the project, we can have a lot of NLOS, non-line of sight areas, right? So in that case, we need to also support communication and sensing in NLOS areas. And in addition, considering a full integration of the two functionalities, we may require to have a joint waveform, right? So based on these points, we're going to have the presentation among these three categories here. And with that, I will start with the first part regarding sensing and tracking at terahertz. So sure, so there's a lot of bandwidth. The question is, how do we exploit this bandwidth? So let's consider, to start with, an OFDM, a system where we can have a large number of subcarriers, right? The problem is that if you have too many subcarriers, right, then also complexity increases, right? Because the idea is to have a large bandwidth to enable a high resolution sensing, but then you also need to process a large number of subcarriers. However, we can exploit the fact that at terahertz, the coherence band may be in the hundreds of megahertz. That means we can tolerate a larger subcarrier spacing, which means less number of subcarriers. That's all good. The problem is that increasing the subcarrier spacing limits the range, the sensing range that we can estimate, right? Because the maximum unambiguous range scales, it depends on the inverse of the subcarrier spacing. The larger it is, then the less the range that we can sense. For this purpose, what partners in the project have proposed is a two-stage maximum likelihood target position estimation algorithm. So in the first stage, assuming there's a band available of B hertz, right? We first take just a B course, a subset of the band, where we have a subcarrier spacing, let's say in this case of delta F. So we focus on the red subcarriers, right? They're contiguous subcarriers, and they have a small subcarrier spacing. So the small subcarrier spaces allows us to avoid the range estimation, the ambiguity in the range estimation, right? But of course, the resolution will not be high because of the smaller bandwidth. And then in a second step, we then exploit the large bandwidth available, but we employ then larger subcarrier spacing. And the ambiguity is avoided because we are only searching within the first, within the area around the first detected, around the range estimated in the first step. Now, with that in mind, we can have a look at some simulation results. So we consider a bistatic MAMO setup. So we have a transmitter and a receiver. We have the objects located within this area. Here we have 200 gigahertz and a bandwidth of 2 gigahertz. And the object behaves like a stationary point-like target, right? And we model, and then it's also modeled the different radar cross sections, which is basically indicating how much energy is being reflected from the object. The parameters of the object are estimated via maximum likelihood, a generalized maximum likelihood algorithm, right? And from the 2 gigahertz bandwidth, we first consider a bandwidth of 400 megahertz. That's in the first step, which I mentioned before. And then in the second step, the largest subcarrier spacing is used to cover the 2 gigahertz. So as you can see from the results here, it's also being plotted position error bound, which depends on the Kramer-Rail lower bound as a lower bound for the performance. And it can be seen here that the root mean square error of the positioning estimate of the object, and as a function of the SNR on the left-hand side, and as a function of the RCS, we can see that it comes very close, near optimal performance, right, to the bound, right? So even for a slow SNR regime, and a very small, relatively small RCS, then it's able to be achieved centimeter level accuracy. And if we go higher than minus 10 dBs, then we can see that it's also possible to achieve millimeter level positioning accuracy, right? So this is just to point out that with this scheme, the ambiguity is avoided, and still a high resolution sensing localization in this case is enabled. Now, we mentioned in the previous part an object that behaves like a point-like target, right? But there are cases where the object size may be large compared to the distance, relative to the distance between the transmitter and receiver and the target, right? In that case, the object can no longer be modeled as a point-like target. In that case, it has to be modeled as an extended target through multiple point scatter. Right? For example, we have this forklift here. So that means that the forklift will reflect at different locations, and then we can model it, like in this case, in the rectangle, different possible point scatters here. So to track the object, right? Why would we want to track the object? We want to track the object because it's a passive device, and we would like to know if it's approaching, let's say, it's in the proximity, or its path is will collide with for example, a nearby worker, and this we can avoid a hazardous situation. So we could track, since we cannot see the object itself, but just the point scatters, right? One could track the point scatters themselves. The problem with that is that if the object is moving, those point scatterers will also, you cannot rely that the same point will also be visible at another location or orientation of the object. But what can be done is that based on the point scatterers estimated at different times, the dimension of the object can be estimated, and what can be tracked is the center of mass of the object, the location and velocity of the center of mass in this case. So based on the point scatterers. And due to this, the tracking of the state vector can be done with a particle filter implementation, given that we have this multiple point scatterers. So based on that, here we can see several simulation results. So now the tracking is of an extended target, right, with different RCS. And this is important. It's assumed that there is random clutter in the environment. So the transmitter is here, and the receiver is here, and the object is here, but there's also random clutter. That means the receiver also collects measurements which do not belong to the object. And then you need to first filter out which measurements belong to the object itself. And there's some assumption about the state vector of the target's parameters, follows a known Markov model. So based on that, here we can see an example where the extended target, the black asterisk here, represents the measurements. And then based on the measurements, then the dimension of the object can be also estimated, right? And more importantly, we can see that the center of mass, which is the red dots here, can be, this is the ground truth, and the estimated ones are the blue dots here. So we can see how the tracking really helps to follow the center of mass of the object, which tells us once we know the size of the object, then we know where the object is and where it can be heading, right? And we can see here that by enabling this tracking functionality, right, the performance of just one snapshot-based estimation is significantly improved when considering the RMSE as a function of bandwidth and as a function of RCS. So it's here we can clearly see the advantage of having the tracking capability here. So now we continue with the second part, now about the waveform. So for the waveform design for ISAC, there are possibly two different possibilities to handle this. We can take a sensing waveform and try to add communication functionality. For example, the most common waveform used for radar is FCMW. The problem with the FCMW is that it does not support data transmission. And if you try to add data transmission capabilities, this results in high complexity or reduced sensing accuracy. Another alternative would be to consider communication waveform and add a sensing functionality. So the most common waveform in wireless communication is OFDM. OFDM has good sensing accuracy, but has high APRs that we'll discuss in the next slide. Another alternative will be to consider some sort of new waveform. Here I list several of them, which are quite interesting, but they face some limitations. Within the THz project, we followed this approach here. So we take waveform based on OFDM, right? As I mentioned before, OFDM has a high PAPR, peak to average power ratio, and this is quite problematic at higher frequency because then the power amplifier efficiency is more sensitive to the high PAPR. And the high PAPR also will reduce the coverage, the sensing range and communication range. Now, an alternative will be to use DFT spread OFDM, which does not face the PAPR issues and has single carrier characteristics, which are attractive through the terahertz frequencies. The problem with that is the DFT spread OFDM has reduced sensing performance. And this is due to the fact that although the PAPR has been reduced, there may be small values in the frequency domain. And then when you try to recover during equalization, you may end up enhancing the noise, which reduces to poor sensing performance. As such, within THz, it has been proposed to use the multi-block DFT spread OFDM. What is the multi-block DFT spread? We basically have then introduced, before the IDFT, which is used for OFDM, several blocks of several DFT blocks, right? So then by playing with the size of the blocks, or the number of blocks here, we can then go from having no DFT. If we have a size of 1, we have OFDM, or we have one big DFT, then we have DFT spread OFDM. So this already allows us to have a flexible trade-off for adapting to different scenarios. Now, based on that, we have some simulation results here for a setup. Here are the simulation, the parameters that have been used for the numerical results. Single antennas are assuming the transmitter, communication receiver, and sensing receiver. This is the performance of the communication to a user in multipath channel. Here, of course, the OFDM has the highest PAPR. Here's the performance of PAPR with QPSK and 16 QAM. Of course, DFT spread, as expected, has the lowest PAPR. And then with the proposed multi-block DFT spread for different number of blocks, we can have a trade-off, right? We can play around coming from here to here. And the same thing happens when we consider the performance of the bit error ratio. So the main point here is that we can enable this trade-off in the communication performance with this multi-block DFT spread. Now, more interesting about the performance of the sensing, in this case, the range estimation. We have 2 point-like objects, which are located at different distances. So we have one strong object and one weak target. And for the equalization, we consider a least squares and a matched filter. And then the actual estimation is performed by the periodogram. So here we can see that although the matched filter is able to estimate quite well the range estimation of the strongest target, it fails to estimate the weak target, right? Whereas the least squares is able to provide a good estimation of the both targets. In any case, the main point here is, again, that the multi-block DFT spread offers a trade-off between the not just communication performance, but also the range estimation, in this case sensing accuracy, between the OFDM and DFT spread or OFDM. So it offers quite a flexible trade-off. Now with that, I then continue to the last part of my presentation, where we target then NLOS sensing. So at higher frequencies, as I mentioned before, we can also deploy a large antenna arrays. And since we have non-line of sight areas, for example, here, the transmitter may be located here. We have an optical here. We're interested in sensing this area here, the so-called region of interest, right? So for that, we can exploit RIST, reflecting intelligent surfaces, right? So if we want to sense this area, we can send a signal here. We can consider a monostatic setup, where we send a signal here, it bounces back here, and it will also bounce back through the RIST. So, but the point is that if we consider this, if we place the RIST in such a way that we are in a near field of the transmitter receiver and the region of interest, then we can exploit the higher rank in the channel, in contrast to the far field assumption of a line of sight channel, which may be only rank 1, to enable then holographic imaging. So then with this near field non-line of sight imaging in an industrial setting, right, we can exploit the multiple antennas here, the RIST here, and we can obtain information about the area here in the non-line of sight to the transmitter receiver. So if we consider the region of interest here, in this case the environment basically, right, for the environment sensing, a pixel-based image. So this is the region of interest with simplified into 8 × 8 cells, and we assume that in the presence of each cell there may be a scatterer or blocker, right? If there's a scatterer, we see this white box here, which corresponds to the intensity of the scatterer. So it has a large intensity. Whereas when here there is no scatterer here. So based on that, we can then consider some simulation results for the near field sensing. As I said, we have this such an example of such an area, and it can be sensed with a transmitter and a RIST and in the near field. So the point is that if the RIST is configured in such a way that the phase profile of the RIST is configured to minimize the mean square error of the image estimate, then you can have an improved performance. So if you just reflect this energy towards the region of interest without any optimization here, it can be seen that there is a poor image reconstruction. Whereas if you try to match the phase profile of the RIS, which is basically equivalent to maximizing the mutual information between the transmitter and the region of interest to the RIS, then for different techniques developed within the project, then we can see an improved performance. Some regularization is also performed because it's an ill-posed problem, and this helps in achieving an improved image reconstruction. With image reconstruction here, we mean basically the environment reconstruction. Right? Now, let me go to the final part. Sure, RIS are attractive, but they require reconfiguration and energy supply, estimation of the channel. They may also require dedicated control channel. So an alternative that has been also considered within the project is the use of metaprisms. Metaprisms have also been introduced for communication in NLOS, and they are passive and non-reconfigurable. That's the main advantage, right? And we can configure them to generate frequency-dependent reflections. So, for example, if the transmitter impinges, this is a metaprism, impinges, sends a signal here. This impinging signal can be then reflected at different angles and at different frequencies, right? So this metaprism has been designed for a 60-degree angle span, for instance. So it will reflect at a certain angle of departure, at the given frequency, at the given subcarriers. There are different subcarriers. So in this way, we can get information about an object here. So the idea is that it's sent through here, and it's reflected back to the same metaprism in a monostatic setup, right? The advantage is that the signal can be shaped and reflected without interaction with the RIS, in this case, the metaprism, right? And configuration of the metaprism can be done depending on the desired angular spread. Now, so here is an example of some results. So the idea is to estimate this object here. Maximum molecular estimation is employed here based on phase profiles used as fingerprints of the object, right? So for example, if you send, and a simple example, if you send a signal here and get some information reflected back from this two subcarriers, then it can be interpreted that there was an object around this angular region, right? So based on that, one can see that the metaprism has a very non-passive, passive device, sorry, fully passive device enables to achieve a high angular estimation. Here we can see different number of subcarriers, and also also the position estimation error, not just the angle accuracy with less than 1 degree of accuracy at 90%, but also a very centimeter level accuracy as well. And it's important here to point out that here we're not employing a MIMO setup here. It's a single antenna access point, but we have this flexibility here, like I said, where the frequency dependent signals are being sent at different angles of the metaprism. And with that, I would like to wrap up my presentation. So here before, I would like to point out again some, you can see some of the partners are being involved and some related dissemination. And also special thanks also to all the THz contributors. And now I would like to answer any questions if there are any. Thank you for your attention.
Thank you, Mario. So far, we have only one. Oh, we have a few questions online now. So the first one is, can you elaborate a bit more on the choice of waveform? So you use OFDM, I understand, but one of the questions, why not use OTFS? And I could even say, why not use single carrier? Because the channel is probably not very dispersive at terahertz.
Right. So, I mean, this is a very good question. And I think I think it's important to not ignore the widespread use of OFDM, right? And that there are, for example, very interesting waveforms I was mentioning here. I did not go into details. These chirp-based waveforms, which are able to have some properties of MCAW, but at the same time, you can modulate data on top of them. They're very, very attractive. But the problem with this waveform is that they have some limitations. And in this case, for instance, they may require additional guard intervals. They have larger out of band emissions. And the question is also, we may be moving away too much from OFDM, right? And then it may be a risk to set up waveforms that may not be considered by standardization, right? So that's what one of the reasons that we focus on OFDM. But of course, we have a single carrier waveform. It's more attractive, and that's why if we have something also not just one waveform that offers single carrier characteristics, but we believe that also having the flexibility in this case, for example, if we have larger DFT blocks here, right, then we have more of these single carrier characteristics, right? So I think it's also important that you're able to tune to the different requirements, right? So for example, one waveform performed like this, DFT spread, OFDM performs like that, and that's fixed, right? I cannot change it, right? But if I start to play with a number of blocks here, right, I can move around here as well as here in the sensing performance. So I'm not sure if that answers the question.
Yeah, I think that's a comprehensive answer. The next question is from Morteza. It's about RIS. He's asking, since a RIS is passive by design, how can we leverage the function as in an active role? Do we have active RIS at the moment? And are there examples of RIS applications that are commercialized already?
I mean, as far as I know there are commercial RIS, right?
Mm-hmm.
So that is, but I didn't get the first part of the question. So that how can, I mean, the RIS itself has to be configured, right? You need to configure the RIS. I mean, here you don't see it here. Okay, no, excuse me. Here you can see the parameter B here. That's basically configuration with the phases of the RIS, right? Here in the other example here, this is a bit different. This is a fully passive device. This device has been designed to have, depending on the configuration of the transmitter location here, to be able to reflect signals at different angles on different subcarriers. So this is something that you design depending on which is the angular spread you want to cover, right? So this is fully passive, and this one is, I don't know, we can call it, maybe it's not active, it's semi-passive because but you need to configure it, right? So I don't know if this answered the question, because I did not really quite get it.
I have also some confusion about the question, but I think it is a reasonable answer. Another question is, if you think about access, right? So a user device, do you think a user device will have this sub-terahertz support? And if so, how many antennas would it need to actually provide a sub-terahertz link?
So if a UE can assist in the sensing, you mean?
Well, not for sensing, but do you foresee that a UE, like a smartphone, would have sub-terahertz capabilities, right? For extremely high rate transmission, for instance. And how many antennas do you foresee a UE device could support to have enough link budget?
Right. Well, I'm trying to make the connection to the sensing part, the data part, but I think that, of course, the number of antennas, right, it depends on the link budget, right? So for terahertz, we know that we're not going to be able to cover probably a large distance, and for that, if you want to cover a larger distance, then of course you will need a larger number of antennas, right? Mm-hmm. For a given number, I cannot give you a number, but what I can think about is that, of course, the advantage is that at the higher frequencies you can scale down the size of the antennas, right?
Right. Yes.
But I mean, trying to relate it to the setup here, I think the point is that you can, in an industrial setup, for instance, of course you can exploit UEs, right, for the sensing, right? But you can also have the access points, right? You can deploy the access points, and there you can put more antennas without any constraint on the device, right? On the space on the device. Yeah.